Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on problem solving on single phase transformer. So now here, the first problem here in this, a 25 kVA transformer. Let me change the color over here. A 25 kVA transformer, 3300 divided by 330 volts single phase transformer has iron losses and copper losses. These are the iron losses and these are the copper losses respectively. Calculate the efficiency at half load and this 0.9 power factor, and also calculate the load at which efficiency is maximum. So now here efficiency equals to X into kVA into 1000 into power factor. This is output. This is the output and this one is the output, and this is the iron loss and this one is the copper loss. So now here X equals to 1 by 2 half load and X equals to 3 by 4 3/4 load. Fraction of load X indicates here. And next, power factor cos phi equals to, what is the power factor? 0.9. And this value equals to 0.976. So now here fraction for half load I am taking efficiency X equals to 1 by 2 and next X equals to 3 by 4. Now here output equals to, what is the kVA value is 50 kVA, 0.5 into 50 kVA and power factor equals to 0.9. That equals to 0.5, 50,000 into P by 0.9, and these are the iron losses and copper losses are 600, and copper losses are variable losses, that is depending on the load. If it is 1 by 4th load, so that is 1 by 4. I square R losses, depending on the load only this losses changes. So now here if substitute all the values, that value equals to 0.976. So the percentage efficiency equals to 96.6. If it is 3 by 4th load, so not 3 by 4th load, so here only half load only. At maximum efficiency condition, the load equals to full load kVA is 50 and this iron losses 400 and copper losses 800. That value equals to 40.823. And next, second case, second problem. In a 25 kVA 2000 by 200 volts and transformer, single phase transformer has iron losses and copper losses 350 and 400 volts. Calculate the efficiency at unity power factor. What do you mean by unity power factor? Cos phi equals to 1. Unity power factor cos phi equals to 1 at half load and 3 by 4. So X equals to 3 by 4 and X equals to 1 by 2 condition, and at this condition calculate the efficiency. So same formula here X equals to 1 by 2 I am taking here, that equals to 0.5. So 0.5 and 25 kVA transformer, and next power factor is 1, and next same thing up to here is okay, and next 350 iron losses are fixed core losses and copper losses are variable, so that is depending on the load 0.5 square into 400 volts. So that value equals to 0.9652. So that equals to 96.52. And next for the 3 by 4th load, only the change is here 3 by 4 and 0.75, 0.75 and 0.7. Remaining values are same. So that value equals to efficiency equals to 0.9702. So that equals to percentage efficiency equals to 97.02. Here percentage efficiency equals to 96.5. Next, a no load ratio of a 50 head single phase transformer means 25 kVA 6000 by 250 volts, and determine the number of turns on each winding. The maximum value of flux is 0.5 Webers, and also determine the primary and secondary turns on full load. So now here this is E1 and this is E2, this one is frequency and this one is a 20 kVA. So primary winding and secondary winding currents we need. So how we will calculate primary current and secondary current? So primary winding turns, here you can determine first. Here how you will determine EMF per turn. We know this EMF per turn. So primary current 2 kVA, this currents here. First here primary winding turns I will calculate it, and secondary winding turns. So EMF per turn E1 equals to 4.44 into 5 into F into N1. So E1 by N1 equals to 4.44 into 5, or E2 by N2 equals to same thing 4.44 into 5 into F, this one. So same thing here, this value for both EMF per turn primary side and secondary side. So this value equals to 4.44 F into 5. Now here 4.4 F equals to 50 Hz and 5 equals to 0.5. So that equals to 11.1 volt. And next thing here N1 equals to this N1, this value equals to 11.11. So now here E1 equals, here N1 equals to this E1 by 11.11. E1 equals to 6000, this one. And next E2 by this value, that equals 22.5. Now here primary number of turns here 540 around, and here secondary number of turns around 22, and primary winding current equals to 25 kVA divided by this primary voltage, and secondary current equals 25 kVA divided by secondary voltage. Primary current equals to 4.167 amperes and secondary current equals to 100 amperes. Now here next question, a 40 kVA transformer, single phase transformer, has core losses, that means iron losses, and 450 and copper losses 850. And next, if power factor of the load is 0.8, now calculate the efficiency and maximum efficiency at unity power factor and load for the maximum efficiency. So that value equals to, so that you need to determine. So what is the formula first here? So now first for the first case here, let me change the color over here. So now here X equals to, so what is the fraction of load? Full load X equals to 1. That is for full load. For full load X equals to 1. For half load X equals to 1 by 2. Now here X equals to 1. This one and this one. 1 is over. So these are the copper losses. This one. And these are the iron losses and core losses. And next, what is the rating here? kVA rating 40 into 10 power 3. And now this, if you simplify this one, that efficiency equals to 0.961. Percentage efficiency equals to 96.1. Now this is the first question. And second question here, maximum efficiency at unity power factor. What do you mean by maximum efficiency at unity power factor? Means here same thing. Power factor is in the previous case 0.8, here is a 1. So power factor is 1, here is a 1. So that value equals to 96.8. And load for this value is, I think this is the 450. At the maximum efficiency condition, iron losses equals to copper losses. So now here copper losses are fixed, means that is 450. So this iron copper losses also 450. The maximum power condition, iron losses equals to copper losses. So that is, this should be 450, I think. Now that value is 96.8. And next, this one is iron losses and copper losses 450 and 850, and full load value is 40 kVA. That value equals to 29.104 kVA. Next case, a 250 kVA, 11 kVA, 11 kilovolts by 415 volts, 50 Hz single phase transformer has 80 number of turns on secondary, and calculate the rated primary and rated secondary currents and primary winding turns and maximum value of flux in the core, voltage induced per turn on secondary winding. So using this given data, you can determine this all this. So first one here. So rated primary current and rated primary second, 250 kVA, 250 divided by, so 11,000 means, so he will get the I1 and this one, and rated voltage, rated primary, rated power transformer rating divided by secondary means you will get. So this is a primary current and this one is a secondary current. Primary current is 22.72 and secondary current is 0.602 amperes. Now here these two are okay, primary winding currents and secondary winding turns. And next here primary winding turns and secondary winding E1 by E2, E2 by E1 equals to N2 by N1. So here N2 equals to 80 turns. So 80 turns on secondary. So N1 equals to 11 E1, E2 and N2. So that N1 equals to this, N1 equals to 2120. Now next case. So now here in this, so maximum value of flux. So the maximum value of flux equals to E2 equals to 4.44 F into 5 into N2. So now here F5M equals to this one. So this is E2 equals to 415, this one. So now here 4.44, 50 Hz, this one. And next secondary winding turns 80. So now the maximum value of flux in the core equals to 23.36 milliwebers. So now here voltage per this one, voltage EMF per turn, this one on secondary turn. So E2 equals to 4.44 into 5 into 5M into N2. So E2 by N2 equals to 4.44 into F into 5M. So you can, this 5M value you can substitute in this, or you can find out 415 volts divided by 80. So this one. So you can solve this problem in two ways, substitute E2 and I2 in this way, or substitute frequency and maximum value of flux in this. So you will get the same value, that value equals to 5.18 volts EMF per turn. And next problem, at 20 kVA, 200 kVA, 10 kVA, 10 kilovolt by 400 volts, 50 Hz single phase transformer and 200 transformer on secondary. Same problem here. So only numericals change. The procedure is same for this. Determine the primary and secondary winding currents and primary winding turns and the maximum value of flux in the magnetic core and flux density at area is this one, 18 centimeters square. So how we will calculate this? Same procedure. This one, N1 you need to find out, N2, E1, E2. We know this. So calculate the I1, I2 and flux density. So this one, A equals to 18 centimeters square means 18 into 10 power minus 4 meter square. So now here I1 equals to this rating equals to 200 into 10 power 3 divided by this is the V1, and next that value equals to 20 ampere, that is I1, and next I2 equals to same rating and voltage is different. So that equals to 500 amperes. Next, here primary winding turns, we know this one, E1 by E2 equals to N1 by N2. If you know the N2 and E1 and E2, we know this. And from this, here E1 by E2 equals to N1 by N2. So now here N1 equals to E1 by E2 into N2. So now here E1 equals to 10,000 and this one is the 400 and this one is the 200. So now here the primary winding turns are here 5000. So now here next case, maximum value of flux. So we know the formula E1 equals to 4.44 F into 5 into N1 or E2 equals to 4.44 F into 5 into N2. So now here this value equals 5. We know this E1 is this one and if frequency and primary winding turns here. So this maximum value of flux is 9 into 10 power minus 3 Webers. And next case here, flux density. Flux density equal this flux. Flux density means B equals to flux per unit area. So now if you know the flux and area, then you can determine easily this is the flux here, this is the area. So Weber per meter square. So now here this is centimeter square is given. So heat is also centimeter square. So flux density Bm equals to 5 into 10 power minus 4 Weber per meter square, that is Tesla. Tesla means into 10 power minus 4. In a 25 kVA, 2000 by 200 volts transformer has iron losses and copper losses 350 and 400 volts, and calculate the efficiency at unity power factor full load and off load. For full load X equals to 1 and off load X equals to 1 by 2, and unity power factor means cos phi equals to 1. So now if you see this formula, here this is the formula for efficiency and here power factor is 1. Power factor is 1 and for full load X equals to 1, and these are the iron losses 350 and copper losses 400, and this is the 25 kVA is the rating. So this efficiency equals to 97.08%. At half load 0.5, 0.5, 0.5, 25 into 10 power minus 3, 25 into 10 power minus 3, 350 and 400. So this value equals to 96.52%. The primary winding of a 25 kVA transformer has 200 turns and is connected to 230 volts, 50 Hz supply. The secondary winding turns and calculate the no load secondary EMF. Full load on primary and secondary currents and flux density in the core. If the cross section of the core is this one is 60 amperes. Now I will draw the circuit first here. This is the transformer symbol. This is the load. This is the supply voltage. Here supply voltage is 230 volts and this is the, now let me change the color over here. So now here primary winding turns here 200 volts, 200 turns, and next secondary no load on secondary winding turns are here. So primary induced, this is 25 kVA transformer, and next this is 50 Hz, 50 Hz, and next thing here secondary turns are 50. So now here no load secondary induced EMF E1 by E2 equals to N1 by N2. This is E1, this is E2, N1 and N2. So from this you can calculate the E2. E2 equals to E1 is 230 and N2 is 50 and N1 is 200. That value is 57.5. primary and secondary currents. So kVA divided by primary current and kVA divided by secondary current. So kVA rating is 25 kVA and this primary current is 230 and kVA rating is 25 kVA and secondary current is 57.5. This value equals to 108.7 amperes and this one is the 434.78 amperes. And next thing here, this the cross sectional area is given. First calculate the flux density is in the question, not flux density. First calculate the flux. So flux density equals to flux per unit area, this one. So now here flux equals to flux by A. So this flux per, so if you know the area then you can determine the flux density. So E1 equals to 4.44 F into 5m into N1, that equals 5m equals E1 by 4.44 F into N1, that equals to, so now here this is 230, this one is a 50 frequency and these are the primary winding turns. So now this is the flux value, 5.18 milliwebers into 10 power minus 3 webers. So now here flux density equals to, this core is here 60 and this one is a flux. So now here flux density equals to 0.863 into 10 power minus 6 Weber per centimeter square. If you convert into the meter square, so in the meter Weber per meter square, that is Tesla. A transformer is rated at 100 kVA. A full load, its copper losses are 1200 and iron losses here 960, and calculate the efficiency at unity power factor and efficiency at half load 0.8 power factor and the load kVA at which maximum efficiency occurs, and the maximum efficiency occurs at 0.85 power factor. So first one here x equals to 1 for full load. So here for full load x equals to 1 and unity power factor, this value is 1. So what about the losses here? 960 are the iron losses and 1200 are the copper losses, and this is a 100 kVA transformer. Now if you simplify this, efficiency equals to 0.9788, so that percentage efficiency equals to 97.88. and next second problem, here this is for half load and power factor is 0.8. So here this power factor is changed and this x value is changed, 0.8 and this is the half load. So everything remaining, this kVA rating, iron losses and copper losses are same. So now here if you simplify this one, the efficiency equals to 0.9694 and the percentage efficiency equals to 96.94 percentage. And next here the load kVA at maximum efficiency. What is the full load kVA? 100. So 100 kVA. So iron losses, these are the copper losses, and that value equals to 89.443 kVA. And next maximum efficiency. So maximum efficiency means here, so this is 0.85. So now here you can take this one 89.43 and 89.43, that only changes are here. And next this value equals to 97.23 percentage. That means any efficiency equals to 0.9723 percentage, efficiency equals to 97.23. A 50 kVA single phase transformer has primary and secondary turns 320. So this is N1 and this one is N2. The primary winding is connected to 220 volt supply and 50 Hz. So calculate the no load voltage, secondary voltage E2. This is E2, and the primary and secondary winding currents I1, I2 and the flux density 5. So now how we will calculate this one? So E2 by E1 equals to N2 by N1. We know very well this formula. So E2 equals to, you need to determine, so this is the primary winding voltage, and N2 20 and E1 is 300. And this value equals E2 equals to 146 volts. And next, what about the primary rating is 550 kVA, and this is primary voltage, and this one is the secondary voltage. Primary winding current is 22.72 and secondary winding current is 33.92. And next, what about this one? The maximum value of flux density equals to, not flux density, flux value. I think this one is flux. If we know the area of the core, then only we can calculate the maximum value of flux density. This is the flux. And next, here E1 equals to 4.44 F into 5m into N1, or E2 equals to 4.44 F into 5m into N2. So here 5m equals to this formula, E1 by 4.4 F into N1. So this is E1, 5 and N1. So this value equals 0.03. This one. So this is a Weber's. Next problem. A 100 kVA 6000 by 400 volts, a 50 Hz, a single phase transformer has 100 turns, and the full load primary and secondary turns, and number of turns on primary. Same thing here in the previous problems we determined secondary turns. Here primary turns you need to consider, and maximum value of flux. Same procedure here. So this is the rating. So 100 kVA, and this is the primary current. I1 equals to kVA rating by primary voltage, and that value equals to 16.7, and kVA rating by 400 volts E2, and that value equals to 250 amperes. And next, E1 by E2 equals to N1 by N2. We know this N2 value, that N2 equals to 100 turns, and E1 and E2 we know this. So from this you can determine the N1. So now here this one N1, so 6000, so 6000 divided by 400 into 100, that equals to N1. So this one here N1 equals to 150 turns. And next, maximum value of flux here, this one. So E1 equals to 6000, and this is 50, and this one is the N1 equals to 1500, I think. So this is 6000, 1500. So now this value equals to 18.01 into 10 power minus 3 Weber per meter square. So now here Weber's only, not flux density, flux only. And next, I hope all these problems are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer your queries. Thank you. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.